Okay, today we're going to talk about conservation of momentum. And conservation of momentum says that if you have a system of two or more particles or two or more objects and they collide with each other, that the total momentum of the system of particles before they collide will be equal to the total momentum of the system of particles after the collision. And this comes about as a result of Newton's third law, which I'm going to show you in this video. But let's just take a look at what the conservation of momentum means. It's like the conservation of mechanical energy, where the energy always stays constant and energy before equals energy after. Well, in this case, momentum before equals momentum after. Not for the individual particle or object, but for the system. In this system, I have two objects, object 1 and object 2. Before they collide, if you look over here on the left of my screen, before the collision, we have a momentum of this first object, which is just m1 v1, and we have a momentum here, which is m2 v2. Now remember that these velocities are vectors, and if you wanted to put this into an equation, you would make one positive and the other negative since they're going in opposite directions. But for now, I'm just going to use the vector notation to show that you have this object has some momentum, this object has some momentum, and if we add both of them together, that's the total momentum of the system before the collision. So this here is the total momentum of the system before collision. This over here on this side, we have a momentum too. This ball or this object has a momentum of its mass times its velocity, and again that would be a vector quantity. This over here, this object has a mass m2 with some velocity v2. Again, if I was plugging in numbers, I'd be real careful that I would say if my right is going to be considered plus, this would be a plus number. This would have to be a negative number because it's going in the opposite direction. Velocity always has magnitude and direction because it's a vector. So if we add up the total, this here is my total momentum of the system after the collision. So in other words, these two come, they collide like two billiard balls, then they bounce back from each other and they go in opposite directions. And what we're going to say is that there's an equation or equality between the total momentum before and the total momentum after. You could set these terms equal to each other, but it's the whole system. In other words, you're adding up all the individual momentum of each, or momenta of each particular object, and when you add them up vectorially, they will be equal before and after collision. So let's see if we can see why this is so. Let's do this. Clear. Should only take a minute. I'm getting better at it, so. Alright, let's consider two objects that are about to collide, and this is mass 1 and mass 2. Mass 1 is moving in this direction to the mass 1 is moving this way. Let's call that the positive direction. And mass 2 is moving the opposite, and here they're going to collide. So here's where they collide, M2. Now what happens is mass 1 will exert a force during this collision period on mass 2. So mass 1 exerts a force, mass 1 exerts a force on mass 2. This yellow is the force that M1 is applying on M2. And it's going to do that for a certain time duration, very, very short. If you picture this as two billiard balls colliding, they don't stay in contact with each other very long. But for that very brief time that they are in contact, one will exert a force on the other one. So let's just look right now. We're concentrating on M1. It's exerting a force on the second one, M2. All right? And this is going to happen for some time interval delta t. So let's look at how the momentum of M2 is going to change. All right? Before, maybe it'll be helpful to do it this way. Here we have M1 moves with the velocity v1 in this direction, and we have M2 moves with the velocity v2 in this direction before they collide, right? So this force of 1 on 2 for a certain time, let's go to our impulse equation. Force of 1 on 2 times delta t is the change in the momentum of the second object, M2. Is going to be change in momentum of object 2. In other words, object 2 experiences a force in yellow, and it changes its momentum. So this is going to be M2 V2 final minus M2 V2 initial. That's the change in momentum of the second ball because the first one is exerting a force on it for this time interval. Now, let's look at what happens here. Ball M2 exerts a force on M1. We'll call this the force from 2 on object 1. And that's going to take place for some delta t. Now you could already notice that the time that they're in contact with each other is the same time. So the two delta t's, whether it's pink or yellow, these are going to be equal. So let's look at the force of the second object on the first one times this time that they're in contact. That's going to be equal to the change in momentum of the first object, because the first object's now going to experience a force which is going to change its momentum. And that change in momentum is going to be M1 V final, V1 final, minus M1 V1 initial. So far so good. We just looked at the force that each ball experienced times the time it experienced it, and we said that's its change in momentum. Now what we want to do is add these two equations together. So we can certainly add these two equations together. And we can notice that by Newton's third law, the force of 1 on 2 is going to be equal to the force of 2 on 1, but 1 is going to be in the opposite direction. So if these are magnitudes, 1 will be the opposite direction. So the force of 1 on 2 is equal to the force of 2 on 1. Action-reaction pair. If that's the case, and you look over here with these two terms, one of these forces is going to be the negative of the other one, and they're going to be equal in magnitude. If one of these is the opposite direction of the other, and they're equal in magnitude, when you add this term here to this term, you'll get 0. And then the 0 is going to simply equal to let's just work with this now. is going to be equal to M2 V2 final minus plus M1 V1 final minus M2 V2 initial minus M1 V1 initial. And if I put that on this side, and notice I take these negative terms and I bring them on over to this side of the equation, we have M1 V1 initial plus M2 V2 initial is going to be equal to M1 V1 final plus M2 V2 final. And what this tells us is the total momentum before is equal to the total momentum after collision. So I don't expect you to work this kind of thing out. I'm not going to put that kind of thing on a kind of a test question, but just wanted to show you that because of Newton's third law of motion, which is interacting forces, one force exerting a force on the other, equal and opposite directions, they will exert forces for a certain time period. The time periods are going to be identical. The forces are going to be equal and opposite. These both forces result in a change in momentum of the object that's experiencing the force. And if you look at those change, you add these two equations up, you will see that the total momentum of the system before then will equal the total momentum of the system afterwards. So we'll do some examples. Should be doing some examples in the next video.